Dear students, this is our 21st lecture on bioorganic chemistry and second lecture on coenzyme chemistry. In the first lecture, we have discussed the biochemical functions of coenzyme A, and in this lecture, we will discuss about thiamine pyrophosphate as coenzyme. Thiamine is a white crystalline compound which is soluble in water and insoluble in organic solvents, fat solvents. And it occurs in the human body as free thiamine or in its phosphorylated form as thiamine monophosphate, that is called as TMP, thiamine triphosphate, which is called as TTP, and from our point of view, the most important one is thiamine pyrophosphate, which will act as a coenzyme in different types of reactions, and this is called as TPP, thiamine pyrophosphate, and this is also known as thiamine diphosphate. So you can see this is the structure of thiamine pyrophosphate or thiamine diphosphate. These are the diphosphate group which is present, which is attached to two aromatic heterocyclic rings. One is pyrimidine ring, this one, and this is a thiazolium ring or thiazole ring which is present in the thiamine pyrophosphate. So this basically is a derivative of vitamin B1, thiamine. So this OH is phosphorylated to give us this TPP as the product. Now, biochemical functions of TPP, that is thiamine pyrophosphate or thiamine diphosphate, which act as coenzyme in decarboxylation of pyruvic and alpha ketogluteric acid in citric acid cycle. Then this is also used in oxidation of other alpha keto acids and two keto acids derived from amino acid metabolism. So this is in citric acid cycle decarboxylation reaction, oxidation reactions, they are amino acid metabolism. All these they require thiamine as coenzyme. So then thiamine pyrophosphate also act as coenzyme in trans-ketolase reaction in carbohydrate metabolism. So we can see the importance of TPP, so that in one metabolism citric acid cycle, this is used for decarboxylation. In amino acid metabolism, this is used for oxidation. And in carbohydrate metabolism, it is used for trans-ketolase reaction. So the mechanism basically is that here the first is that conversion of pyruvate to acetyl coenzyme A, which is catalyzed by pyruvate decarboxylase enzyme, which is a enzyme complex consisting of these three: pyruvate decarboxylase enzyme, dehydrolipolyl transacetyl acetylase, dihydrolipolyl dehydrogenase enzymes, and all these three enzymes, they do different types of functional group transformations. So for example, if this is the keto acid which is used as substrate, this E1 enzyme pyruvate decarboxylase will be used up for decarboxylation of this. So in presence of thiamine pyrophosphate, that is TPP. So when this enzyme, coenzyme complex of pyruvate decarboxylase and thiamine pyrophosphate, they react with this keto acid. This keto acid will undergo decarboxylation and we will get this type of intermediate. This will be reduced to OH and enzyme substrate complex will get attached to this substrate. So this is substrate enzyme coenzyme complex will be formed, and then this enzyme coenzyme substrate complex will undergo reaction with this lapuolate, and this will transfer acetyl this acetyl group to this as sulfur sulfur bonded cyclic structure into this intermediate in the presence of enzyme transacetylase. So acetyl group is transferred from this to this substrate with this enzyme, and we will get this type of intermediate. And then this in the presence of coenzyme A, this acetyl group will be transferred to coenzyme A. We will get acetyl coenzyme A, and these types of dithiols they will be formed. And then these dithiols they will undergo dehydrogenation in the presence of enzyme dehydrogenase E3. So in the presence of E3, one H from here, one H from here, cyclization will take place to give us this product. And then these two hydrogens they will be used up by FAD, and this will become FADH2. So this will act as coenzyme in this case, and this enzyme coenzyme complex will be formed. So this is how the TPP will function in these types of transformations. So this is the mechanism, and this is the pyrimidine ring, this is the thiazole ring, and this is the diphosphate present. In the first step, the H proton will be removed at this place. This proton is removed to generate this type of thiazolium carbanion, and this carbanion will attack this carbon, which is electrophilic in nature of the keto acid, to give us this type of tetrahedral enzyme substrate complex. And then this will undergo decarboxylation at this place, and a carbon-carbon double bond will be generated with the neutralization of the charge at this nitrogen. We will get this type of intermediate with carbon-carbon double bond. Then this will act as a nucleophile, and this will attack this sulfur-sulfur bond, and ring opening of this breaking of sulfur-sulfur bond will open this ring, and we will get this type of intermediate. And then this will undergo removal of the proton from here and breaking of this carbon-carbon bond to regenerate back this carbanion, which will again react with the keto acid for decarboxylation. So this is how thiamine reacts with the different types of keto acids for their decarboxylation. Then action of alkali and acid on thiamine pyrophosphate. The hydroxide ions they are added to the carbon 2 of the thiazolium ring in alkaline solution, which will yield an unstable pseudo base. Through this cleavage of CS bond, this will form a colorless thiol form, and the amino group of the pyrimidine will react intramolecularly with the C2 in the thiazolium ring, and we will get a tricyclic intermediate which is called as dihydrothiachrome. And for all these reactions to take place, the pH of the reaction must be alkaline, that is more than 11 in this case. Then ionization of this dihydrothiachrome will take place with the opening of the thiazolium ring to give the yellow thiol form. And this yellow thiol form can be converted into colorless thiol form uh, with the degradation of hydrogen sulfide and a mixture of breakdown products. Similarly, under acidic pH, the if thiamine solution is heated, then cleavage of the methylene bridge between the pyridine ring and the thiazolium ring will take place. And the pH of the reaction should be less than 6 in most of the cases. So these are the various reactions. This is our TPP. So if we heat this, the breaking of this bond will take place at this place, and we will get thiazolium ring and pyrimidine ring. They are formed. Now when this TPP reacts with hydroxide ion at pH more than 11, then we will get this white form of TPP. White intermediate will be formed, and this will be formed with this nitrogen acting as a nucleophile and adding to this carbon to generate this type of uh, carbon nitrogen bond will be formed. This will undergo cyclization, and this positive charge on nitrogen will be neutralized, and this structure, neutral structure, is called as white intermediate. Or this white intermediate can be converted into yellow intermediate or yellow or thiol form by breaking of this ring. So when hydrogen is removed in the presence of OH negative, this hydrogen will be removed, and this nitrogen will act as a nucleophile. This will form a carbon nitrogen double bond at this place, and this carbon sulfur bond will break, and we will get a sulfur negative charge. And this type of yellow product will be formed with the breaking of this thiazolium ring. And this thiol form, yellow thiol form, can be converted into colorless thiol form very fastly when hydrolysis of this bond will take place. This will be converted into aldehyde part, and this nitrogen on hydrolysis will give us amine. So this is the colorless thiol form. This is the yellow thiol form. In yellow thiol form, this is formed from the white intermediate dihydroxythiochrome on breaking of this bond, thiazolium ring. Whereas this yellow form gives us colorless form with breaking of this carbon nitrogen double bond. Six-membered ring. This six-membered ring is broken, undergoes hydrolysis. Then this thiol form undergo removal of H2S to give us H from here and H2 from other place. We will get this type of intermediate by removal of hydrolysis of this H2 from water. As from here, water will add to this carbon-carbon double bond, and we will get ketones as the product with the removal of H2S gas. And then this form can undergo condensation reaction to give us benzodiazepines as the product. So these ketones, they will undergo condensation reaction with this amino group, and we will get 7-membered ring compounds like this. Or these colorless thiol forms, they can undergo hydrolysis with the breaking of this bond, and we will get these types of amines and thioketones as the product in addition to formation of the formic acid. So these are the different types of products which can be formed under acidic or alkaline conditions from TPP. Then similarly, TPP can undergo oxidation and reduction reaction as we have seen in the previous slide, that yellow thiol form and the intermediate precursor, they can be oxidized to thiochrome. So this yellow thiol form can be oxidized to this thiochrome. Basically what happens is this sulfur will act as a nucleophile, will attack at this carbon, and this double bond will be converted into a single bond, and H positive will add to this nitrogen. We will get these types of intermediates, and these will undergo oxidation with the removal of this hydrogen from this place, and this will form a carbon nitrogen double bond. We will get thiochrome as the product. And similarly, these intermediates which we have seen in the previous slide, they can be oxidized to disulfides by dimerization of these two, or these can react with sulfides to give thiols, and in addition we can get disulfides of these compounds. So this is how oxidation and reduction reactions of different forms of TPP which have been formed under alkaline conditions, they can be formed. Thank you very much.